It's electric. And I kind of have a joke here, woogie woogie woogie, which is in reference to a funk song from the 70s. But this is an introduction to some electrical characteristics. Electricity defining our everyday life. You see, the uncovering of how it is that electrons move has revolutionized our lives in so many ways. I want you to just take a moment and think about how many things around you rely on electricity and how those things improve your life. All right, let's define something. Electricity is the movement of the electrons. It's not the electrons itself. It's the fact that electrons move that we harness the power and the energy. This is very different than static electricity, in which the electrons stay in one place. And here's a little animation. If you take a look, you see the atoms of a conductor, and the electrons jump from one atom to the next. How fast this happens is a characteristic we're going to take a look at. But in essence, all electrons are essentially the same, and they just jump from one atom to the next. This is electricity. So let's define quite a few concepts here. The first thing I'd like to define is this idea of a conductor. Conductors are materials that electrons can move easily through. The electrons jump from one atom to the next very, very easily. Some examples of conductors, most metals, and most notably copper, are conductors. Salt water, so seawater, and the human body can conduct electricity as well. The flip side of that is an insulator, and these are materials that electrons cannot move through or have much difficulty moving through. So if the electrons cannot move through this material, we call them insulators. Some examples are plastics, rubber, air, glass, among others. So that kind of leads us to ask, why would people build wires like this with copper on the inside and rubber on the outside? Does this allow electrons to move through the copper easily, but then protects the people touching the wire from electrons moving outside? Which is why wires are built with copper centers and rubber insulation on the outside. Now we're getting into three characteristics of electricity. And the first one is called electric potential energy. And I think if you recall, potential energy is what could be. Earlier on in our physics class, we saw that potential energy dealt with picking things up. And eventually that energy could become kinetic energy. When talking about electricity, though, electric potential energy is more commonly known as voltage. And it is measured in this unit's volts, capital V. Electric potential energy is the force that has the ability to push or pull electrons through a material, which is usually a conductor. You can think of it kind of like a pressure. And here's a great little GIF showing an analogy, which is a story that conveys an idea. As this person pulls a bucket out of the pool, you see water gushing out the side of the bucket. And this is a very common way that teachers try to express this concept of voltage. One way to think about voltage that tends to help students is to use an analogy, which is a story that illustrates an idea. So when we're talking about voltage, can we think about what happens to water inside of a bucket? So for example, if I have a bucket almost full to the top of water, that water doesn't move yet, but there is a very high pressure available. And it's this pressure that is very similar to the pushiness that electrons feel in the form of voltage. Now, if I were to poke some holes in the bucket, one near the middle and one down near the bottom, the water would behave differently coming out of that bucket. The water coming out of the top hole would only dribble out because the water is pushing. There's a very small amount of water pushing the water out of the hole. And this is pretty good at visualizing what low voltage is like for electrons. If there's a little push, you get a little bit of electrons. But on the alternative, if I poke a hole in the bottom of the bucket, you have all of this water pushing the water out the hole, and you get high voltage or high pushiness of electrons. And so this is the way that a lot of teachers explain the concept of voltage. The next definition I would like to talk about is current. It has the symbol of a capital I. Now most students at this point ask, Mr. Fay, why isn't it C? We already have something, coulombs, represented with a C. So to distinguish between the two, we use the symbol capital I. And it is measured in a unit called amps, if it's written out, or A. Current is the number of electrons that pass a point in any given amount of time, and that given amount of time is usually 1 second. In fact, that is the definition of current. 1 amp equals 1 coulomb, which is a measurement of charge, divided by 1 second, which is a measurement of time. What's cool is we can use water again as an analogy to explain current. In 2018, the Special Olympics dropped 60,000 rubber ducks into the Chicago River as a charity event. Now, this was a bit of fun in order to raise money, but it also gives us an opportunity to look at these rubber ducks as if they were electrons. So as the rubber ducks moved down the river, we can see a situation as they cross this blue line. On the top, you see a low current. There are very few ducks per second. On the bottom, we have a high current. There are many, many ducks per second. Well, the same thing happens in an electrical wire. On the top, in the red box, we see electrons moving from one atom to the next. If I put my blue line in here again, we'll see in the red box that these electrons don't pass the blue line very much. This has a low current, very few electrons per second, maybe 0.7 in 1 second. In the yellow box, on the other hand, we see a very high current, lots of electrons passing this blue line in 1 second, maybe 3.2 in 1 second. Resistance is the last characteristic we're going to talk about in this lecture, and its symbol is capital R, like you would assume. It's measured in ohms, after George Ohm, but has this funny looking symbol. I call it the upside down horseshoe. It's a Greek letter, and it means ohm. Resistance is the ability of a material, or the shape of that material, that allows electrons to pass through it easily. Now, if you have something that has a low resistance, has small ohms, that means that electrons can move through it easily. And kind of by definition, that's a conductor. If you have a material with a high resistance, or a high H, a big H, ohm, electrons cannot move through it easily. And by definition, that's kind of considered an insulator. But if you haven't figured out a theme, let's go back to a water analogy or story. If I had 2 buckets, one bucket very, very full, and one bucket not very full of water at all. What would happen if I put a pipe between these buckets? Would the water start flowing? Yes. But it's the size of the pipe that actually matters quite a bit. If you have a thin pipe like this, you will get movement of water, but there's a very high resistance. In other words, there's not that much room for electrons to move from the high bucket to the low bucket. It's hard for the water, it's hard for the electrons to move from one to the next. But if I have a very thick pipe like this, more water will flow quickly, just like more electrons will flow between this pipe in order to move into this next bucket. Eventually, all the pressure in our original bucket, all the pushiness, is going to be equal to all the pushing or pulliness in this bucket, and electrons will stop flowing. All right, let's wrap it all up. Let's put it all together. All of these characteristics are related to each other in what's called Ohm's law. And basically, Ohm's law says that voltage equals current times resistance. Or another simpler way of putting it is V equals IR, which is useful when we start talking about the characteristics of electrical circuits.